lecture, I started with the coordinate transformation between inertial and accelerated frames, introduced the idea of horizon, and then sort of promised you that this will be linked with the concept of temperature very soon. And I gave a small introduction to that idea in terms of classical exponential redshift of waves in the presence of a horizon. Then we just started on quantum field theory because I need quite a few concepts in quantum field theory which I want to develop before I go and combine these quantum fields with non-trivial methods. When we started, I pointed out that one way of motivating quantum field theory is to say that if you have a relativistic particle which propagates from one event to another, and you want to do a sum over all paths connecting these two events, relativity requires you to treat time and space at the same footing. So just as a non-relativistic particle can go back and forth in, let's say, y coordinate, a relativistic particle can go back and forth in the time coordinate, which in turn implies that at a given coordinate time, a single particle can be in infinite number of places. So if you insist, as we all like to, that the evolution should be described by some kind of a Hamiltonian which gives evolution from one t equals constant surface to another t equals constant surface in the coordinate frame without worrying about the proper time of the particle, then it is important that at any given time t, I need to be able to handle infinite number of degrees of freedom. So one way of dealing with this infinite number of degrees of freedom is to use a field. And we also need to be able to allow for the number of particles to change from instant to instant. And that can be most easily done since we want energy to be quantized in integer units of this number by introducing a bunch of harmonic oscillators. So at this stage, this is all in some sense motivational. At this stage, I said that there is a very interesting mapping, which let me write down once again. Consider an action A for a whole bunch of harmonic oscillators, infinite number of them in fact. I'll write it as ddk over 2 pi d whole to the power d. D is the dimension of space times integral over time, which is dt, times the Lagrangian for a single harmonic oscillator, which I will write as half qk dot square. The modulus will be clear in a minute. Minus a frequency half omega k square qk square. This system knows nothing about fields or relativity. This is essentially the action for a harmonic oscillator labeled by a vector k. In fact, it is the action for two harmonic oscillators labeled by a vector k, because this qk in general could be complex. So it has a real part and imaginary part which can be separated out. But that is a minor issue which we don't have to worry about. Then I am summing over all values of k. And since k is continuous, I am integrating over dd. Okay? So this is an infinite number of harmonic oscillators which you have. The system is completely specified by specifying this function omega of k, which is the dispersion relation for this system. What is remarkable, which we will spend a little bit of time on, is that this can be put in one-to-one correspondence with another system which has the action which is minus half integral d plus 1x, or let me again write it as ddx dt. Half I have already taken care of. di of phi for a scalar field phi, and this has a minus, because of my signature is minus plus plus, this has a minus sign in the phi dot square term, which is taken care of with this minus to give positive kinetic energy, and it has a plus sign in the del phi square, so I could have added an m square phi square to that. Now let us look at this system. This system describes a field phi of t comma x, and if I Fourier transform this field in space and write it as integral ddk over 2 pi to the power d qk of t e to the I k dot x, I can specify this either by this function or by this qk of t, and if I plug this into this and work through the algebra doing the spatial integrations, I get back exactly this. Okay? So a system which is made of this field, which is completely relativistically invariant. We are talking about special relativity in inertial Cartesian coordinates for the moment. We will introduce complications later on. Such a theory can be mapped to a theory involving an infinite number of harmonic oscillators. Now a few minor points which we will take care of right away so that we don't have to come back to that. The first point is that this will of course work only for a particular dispersion relation. And the dispersion relation which we need here is just omega k square equals k square plus m square. This is nice because this allows me to identify k with the momentum of the particle and omega, h cross omega with the relativistic energy of the particle. The second point is that since I want phi to be a real scalar field, this qk satisfies the condition q star of k is q of minus k. So only half the k vectors are really independent. The rest are mapped back, which essentially says that this degeneracy of real and imaginary parts here can be taken care of. So if you just don't try to be too careful about it and do the naive things, it will all work out fine. Okay? So that doubling of the degrees of freedom will be taken care of by the fact that there are 2 degrees of freedom for every k here, and you just stick to one particular set of k. So we will not worry about it. But what is remarkable is that a system like this, which I emphasized last time, could be describing magnons in a solid, a magnetic solid, and the excitations of that system would be described by a dispersion relation. And you can think of it as number of magnons and the scattering of magnons, etc., etc. Is a very general framework. The relativistic invariance is brought into the theory only through this relation, which, this being quadratic and this being a quadratic term, allows you to describe massive excitations above a ground state. Fine. Now having done this much, now suppose I want to study quantum theory. So far everything has been classical. Now suppose I want to quantize this system. How do I do that? First I do this Fourier transform. Then I know that the system has been reduced to an infinite number of harmonic oscillators. As long as the infinity doesn't scare me, I know how to quantize one harmonic oscillator, then I can quantize infinite number of harmonic oscillators as long as they are not interacting with each other. And they are not interacting with each other here. So in particular, a given state of the field, the quantum field, can be written as a product of the quantum state for each of the oscillators. So just as an example, let us write down the ground state. The ground state of the system can be thought of as what is known as a ground state functional, which can be written as a product over all k of the ground states, let us say phi naught. Okay, phi is a bad notation, so I will use lowercase psi naught of each of these harmonic oscillators. Okay, by which I mean the real and imaginary part, but as I said, if I don't worry about it and think of it as real variables, everything will take care of themselves. So this will look like, this will be proportional to exponential minus half. The product here Each of the harmonic oscillators is a Gaussian. So the product here is going to be a sum in the exponent, and which I can replace by an integral. Integral ddk over 4 pi d power d omega k qk square. So here I will reintroduce the modulus so that it has the states for both the real and imaginary parts of it. So this is the functional. So what does that mean? Suppose you say that the state is in the vacuum state, which is the ground state of the scalar field, and you want to know what is the probability amplitude for the field to have a particular configuration. So you give me a configuration phi of x, I am supposed to give you a probability. So the moment you give me this phi of x, I will Fourier transform it, then I will get these qk's, then I will go and compute this quantity. That gives me a number. Now the relative probability, since we are not worried about the normalization, the relative probability for one particular field configuration to exist in the vacuum with respect to another field configuration is just the ratio of these two numbers. Okay? Now I like this kind of an approach using what is known as the Schrodinger functional method, because it makes very clear to you that the vacuum has lot of activity in quantum field theory. In the vacuum, there are non-trivial field configurations. Any field configuration which you want to think of can exist, and you can compute the probability for a given field configuration to exist. And that is all encoded in this. In fact, this can be written in a slightly nicer form, which we don't need, but I might as well do that. The trick here is that, let us look at the massless field, so m is equal to 0. So this omega k will become just mod k. And I would like to write it entirely in terms of the field itself. To do that, you look at that quantity in the exponent. So this is an integral over ddk this is modulus of k. So I am going to multiply it by another k and divide by a k. So this is mod k square qk square. Now you know that k square qk square is essentially the del phi in the Fourier space. So if you write it as the Fourier transform of del phi, the whole thing becomes a convolution integral, and you can work that out. And you will find that the answer in 3 dimensions, so this is 3 here, in 3 dimensions, will turn out to be something like 1 over 2 pi square integral d3x d3y, because it is a convolution, a Green's function g of x minus y del phi at x, this is at x, dotted with del phi at y, where this g of x minus y here, I have normalized it in such a way that g of x minus y here is just 1 upon inverse square of this distance. It is just 1 upon modulus of x minus y the whole square. Okay, the details you will find in the notes. So I can plug this back here. So in this particular case, the ground state wave functional just becomes exponential minus 1 upon, I think this is, I'm not sure about the factors there, it may be 2 pi square or 4 pi square, I'm not quite sure about that, but that you will find in the notes. Integral d3x d3y, actually I think this is 1 by 2 pi square if I remember right, so this is actually 1 by 2 pi square. Yeah, 1 by 2 pi square del phi dot del phi. One is at x, the other is at y, divided by x minus y the whole square. So what does this mean? This expression is still nicer because I started with a ground state functional entirely in terms of phi of x, and you have given back the answer in terms of that. You give me any field configuration, I compute this quantity and integrate this. That gives me the probability amplitude for that particular field configuration to exist in vacuum. If you want to really see a non-trivial effect, what you should do is to repeat the same analysis by changing the boundary condition. For example, suppose I put two plates at 0 and L, and I say that the field has to vanish at 0 and L. For a scalar field, this is not very well motivated, but if you are thinking of electromagnetic field, then this is what would lead to Casimir effect. So you have two capacitor plates, plain parallel capacitor plates at 0 and L, and you are saying that the relevant physical degrees of freedom has to vanish on those plates. What it changes is this fundamental Fourier transform, because you can't do e to the I k dot x kind of running waves at that stage. Instead, you will use some kind of a sine kx kind of a mode with kn being n pi over l. Then you redo the whole thing, you will find that this Green's function changes. So you will find now, if you repeat that analysis, which is given as an exercise in the notes, the final expression can again be written as exponential of some object like this, but with a different g. This is again very nice because it tells you very concretely that if I introduce two plates, or rather if I change the boundary condition, the vacuum functional changes. The probability amplitude to have a given field configuration phi of x is no longer the same now. Okay, the moment you have introduced the plates, it has changed, which it should be, because for example, if I take a field configuration which is not vanishing on the plates, I should now get 0 amplitude for that to exist. But it modifies all the field amplitude. So what we think of a vacuum in the presence of plates is different from the vacuum in the absence of plates, which is not very clear when you use the standard canonical quantum field theory, because you have creation and annihilation operators for different oscillators and you keep thinking of it as a vacuum. But this tells you that the vacuum is very sensitive to the boundary conditions which you are using, and when you change the boundary condition, the vacuum functional changes. And this is going to be a running theme in our talk, because you will find that what an accelerated observer will think of as a vacuum is different from what an inertial observer will think of as a vacuum. And that is going to be behind all these thermal behavior, etc., etc. So this is essentially to warm you up to that. And now we will go further and do a little bit more on quantum field theory, but again using quantum mechanics as a prototype. So what I want to do next is to orient you towards a few results which we need from the path integral formulation. I'm going to assume that all of you have some kind of a noding acquaintance with path integral, but the important results which I need, I will derive. The basic idea in path integral formalism is that you can study the dynamics of a quantum mechanical system by separating out the initial conditions. That is, if you want to know what is the wave function for a system at time t, dependent on some degree of freedom q, you can write it, because Schrodinger equation is a linear equation, as integral over, let us say, dq1 minus infinity plus infinity, in the simplest context, k some q, some t comma q, semicolon, t1 comma q1 times the wave function psi at t1q. So if you give me a wave function at some time t1, then I can give you the wave function at a later time by integrating with a kernel k here and integrating out this dq. Okay? So this kernel is what I need to find, and this kernel controls all the dynamics, and this is the initial condition. So as far as the dynamics goes, I only need to determine the kernel. And there is a prescription to determine this kernel. So this kernel, which I will condense the notation, okay, for the moment I will leave it like that, q, from some point 1, which stands for q1 t1, that is just to save some writing, can be thought of as a sum over all paths. Here is where the path integral comes in, of exponential I times the action, where the action is evaluated as an integral over a Lagrangian with exactly the same boundary conditions. The upper limits are p comma q and the lower limit are t1 and q1. Okay? So if you know the action for the classical system and you can perform that path integral, you know the kernel, and once you know the kernel you can calculate all of this. We will be interested in systems in which the Hamiltonian is time independent. So if the Hamiltonian is time independent, then we also know that there is an equivalent description in terms of the energy eigenstates. So the H acting on some phi n, which are the energy eigenstates, is some En phi n. Using this, you can find a simpler expression for the kernel, which is going to be quite useful. And we will have to switch back and forth between the action expression involving the action and an expression involving just energy eigenstates. So let me derive that part. To do that, what we will do is to just rewrite this minus infinity plus infinity. Okay, let me not rewrite that, but I'll just work that out independently and compare with this. Suppose you are given this wave function and you expand it in the energy eigenfunctions. So we know that the initial wave function, the final wave function psi of t comma q can be thought of as arising out of this expansion, let's say over n, some Cn phi n of q e to the minus I En t minus t1. That is, I start with at t is equal to t1, this phase goes away. I start with a psi 1 and then I expand it in terms of the energy eigenstates phi n of q, thereby determining this Cn. Then at any other later time, I only have to put this phase factor to find the evolution. So I have to now express Cn in terms of the initial quantities, which I can do. So this is also equal to summation over n. I'll write Cn as integral minus infinity plus infinity dq1 times psi of q1 t1 times phi n star of q1. This is the standard expression for the Cn, that is, if I put t is equal to t1, this is essentially what will come out of here. Then I have to put in the rest of it, which is, this is Cn, then I have a phi n of q e to the minus I En of t minus t1. So if I compare this expression in which I pull out this dq1 out and the psi q1 t1 out, what remains is just this kernel. That is, you compare these two expressions and you can identify what k is. So that k is given by k tq t1 q1 is given by summation over n phi n of q phi n star of q1 e to the minus I En t minus t. This is an extremely useful formula, as we will see. Okay. What it tells you is that if I have a system with a Hamiltonian head and I know all the energy eigenfunctions and energy eigenvalues, then the dynamics which is decided by the kernel can be expressed in this form. It's called the Feynman-Cake formula. So you can write this thing. Why is it useful? It is useful because we have an alternative description for the kernel, which is sum over paths exponential I times the action. So if somehow we can compute the kernel, say by approximating this path integral or by some other method, then this allows you to determine the states of the system and the energy eigenvalues. And in particular, it allows you to determine the ground state in a very nice way. And we are going to work with ground states for many of these systems, so I want to obtain that formula. To find that formula, we first notice that everything depends only on this difference. And we are going to analytically continue in the time coordinate to imaginary values of time. So this, when I do the analytic continuation, this formula becomes summation over n phi n of q phi n star of q1 e to the minus en, let us say capital T, where my T is defined as I times T minus T1. So I have rotated from real axis in time to imaginary axis. So the small t becomes I times t and t1 becomes I times t1, and the time difference in the Euclidean sector I am denoting by this capital. I can also do without any loss of generality, it turns out to be convenient, to set the ground state energy of the system to 0. So we will assume it's a bounded Hamiltonian and there is a ground state energy, and I will add or subtract a constant to the Hamiltonian so that E0 is equal to 0. Now you look at this formula and suppose I now take the limit of capital T going to 0. So by this we have already got into what I would have called the Euclidean kernel, so I will probably write it as Ke of T Q starting from 0 and the Q. Okay, this is the formula we have. Now if I take the limit of capital T going to infinity, in this sum, the term which is going to have the leading behavior at late times is the one in which En is 0. Okay, everything else will be suppressed with positive energies in a bounded Hamiltonian. So the coefficient of that will essentially have the ground state index. So I can formally write that if I take limit capital T goes to 0 of, let us say, K, let us take K with a T and let us put that Q to be 0 and then take 0 some Q1. Okay, I have put that Q also equal to 0. This is going to be essentially phi 0 of 0, phi 0 of Q1, e to the minus ENT. This E0 is 0, so that is not contributing. And this is just a normalization constant. So this means that this quantity is proportional to the ground state wave function. So let us just make sure we understand what we have done. Somehow we compute, let us say, this path integral and obtain this kernel after doing the Euclidean continuation. So you get this expression for the kernel. In that expression, if I let t go to infinity, I get an expression like this, and that will give me the ground state wave function of the system. Of course, if you only want t going to infinity, t can be taken to go to infinity either by setting t1 equals 0, which is what I did here, and letting this t go to infinity. Alternatively, I could have taken this t to be 0 and let this t1 go to minus infinity. So I could have written down another formula here, which is same as this, with it will be k. Instead of this, I set equal to 0, and I keep that as q, and then I let this to, let us say, minus infinity, and I set this to 0. That is also would have given me the same result. Either of this would lead to this. And incidentally, I didn't put a star here because we are thinking of non-degenerate sensible ground states which are real. So the complex conjugation is not required. So by taking infinite time separation in the Euclidean sector, I can pick out the ground state wave functional from the curve. Everything I have said here carries over to a field theory. Okay? We said we are doing sort of point quantum mechanics. So we are working with things like Q1, etc., which is like a single degree of freedom. The generalization goes in two steps. First, you start with a system which is, let us say, Q is the dynamical variable, and you go to a set of discrete variables like Q1, Q2, etc. That is obvious because we are still doing point quantum mechanics with several degrees of freedom. The only changes would be in this integral, for example, if there are several of these degrees of freedom, you have to integrate over all of them. It will depend on all of them, no surprises there. Then you quietly go from there to an infinite number of these by saying that this Q is actually a field configuration. So the idea now is that at every take a given time slice, take any point in space, the field there gives me the dynamical variable. So instead of specifying this Q, I specify this functional, the field configuration. Then everything I have written down, all the formulas continue to be valid. For example, this formula will have a Q of x here, Q1 of x here. This will be the wave functional of Q1 of x, and the integral over dq1 will be a functional integral over dq. Okay, so you have to formally define that functional integral, but as far as the mathematics goes, this is what happens. Yeah.
So I'm still confused by this t going to 0. I mean, that should be t going to infinity, or like completely.
This one?
Yeah. So
or this one?
No. So
okay.
The upper limit.
This should be infinity, but I wrote here t going to. Yeah, this is wrong. T going to infinity. That's correct. Yeah, I made a mistake. So this should be in the limit of capital T going to infinity. We pick out the ground state, and that I can either do by putting this to infinity or this to minus infinity. That's all it's. Now if you look at this formula, as I said, there is just a functional integral. Let us come to this one, which is what we will be using, and it's which came out of this. Here, this phi n of q will now be the wave functionals describing, let us say, the nth state of the field. If you think of free fields, the nth state will be for each of the oscillators to be in some excited state. And then you will again have a phi n of q of x here, and phi n of q1 of x here, and you will do exactly the same kind of summation. So the kernels will now be functionals of q of x and q1 of x. So except for that, everything which I have done will go through. So I will not even bother to denote whether I am doing field theory or point quantum mechanics, because the mathematics will take care of that in this notation. So whenever I write q, if I am doing field theory, it is q of x, and if I am doing point quantum mechanics, it is either a set of them or one of them. Okay? So this is what we have. Now that we have introduced this transition to imaginary time, I also want to describe another example which will turn out to be useful, where this arises very naturally. This is in the case of studying finite temperature systems in statistical mechanics. So let me introduce that too, and then we are almost done and we can start doing what we wanted to really do. Okay. So the easiest way to understand that would be to think of a system which is in some temperature, and the system has different energy levels. Now if the system was in zero temperature, then if it is in the nth energy level and you want to study the expectation value of some operator, let me call this let us say O. O is some operator built out of some dynamical variables Q, let us say, and I want to compute its expectation value. If it is in some given energy eigenstate, I would have just computed it by saying integral dq phi n q square times this O of q, if it depends only on the dynamical variable. Otherwise you take the expectation value in the sandwich between the two operators, etc. So this is the standard expression, and this is what happens in zero temperature. But now suppose I say that, well, I don't know in which energy state it is, but there is a probability amplitude, there is a probability, statistical probability, that it is at an energy state En with e to the minus beta e. Then I can throw in this as well, and sum over all n and divide by the partition function. Let us again pause to see what we have done. We have done two kinds of averaging here. If the system is in nth eigenstate, then the expectation value is just this integral. Then the probability that it is in the nth state is e to the minus beta en. So you multiply by that. And then you take the average over the statistical average over that as well. So there is a quantum mechanical average which is given by an integral over dq of this. And there is a stat-mech average which is obtained by saying e to the minus beta en divided by 1 upon the partition function. So both are combined. Now there is a slightly nicer way of writing this which we want to introduce. So to do that, let us look at it as, let's keep 1 over z. Then I have a summation over n integral minus infinity plus infinity. Let me write this mod phi n q square as phi n at q, phi n star at q, in fact let me interchange the summation and integration. E to the minus beta en the operator O of Q. Okay, I haven't done anything. I just expanded this out and rewritten it a little bit. This I can think of by introducing an object which will turn out to be a density matrix. I first introduce a density matrix by definition rho of q prime, which is summation over n phi n of q, phi n star of q prime, e to the minus beta e. This is just a definition. But given this definition, this equation becomes 1 upon z trace rho O. Let us try to understand what it means. Suppose I am given all the eigenstates of this system, then I can of course construct this object, which is phi n at q, phi n star at q prime, e to the minus beta en summed over odd n. Once I have constructed this object, this entire quantity here is just the diagonal element of that matrix, treated as q and q prime as the two matrix indices, continuum indices. So this is just the diagonal element of that. So for any given operator, this is already in the diagonal representation of q, so I can write this as trace of rho times rho. Okay? So the expectation value of a quantity, an operator like this, can be thought of as just the partition function times trace of this. Right? Now, in this particular way, I have defined things. If I have just put q is equal to q prime, I am integrated. That is, if I have taken the trace of rho itself, I am taking these two to be equal and integrating over q. I would have put these two equal, so it is mod phi n square. Integrating over q, because it is normalized, will give me unity. So this is going to give me just summation over n e to the minus beta e, which is nothing but your partition function. So this formula itself can be written as trace rho o divided by trace rho, which is of course obvious. And very often you will work with what is called a reduced density matrix, where you would take this rho and divide by this trace rho, or work in a representation where trace rho turns out to be unity. Okay? But that is just a window dressing. So essentially, if you are dealing with a system which requires both quantum mechanical averaging and thermal averaging, then it is convenient to first construct this quantity called the density matrix or the canonical density matrix, and then calculate expectation values by this. Of course, the way I did that, I just chose a simple operator which depends only on q, but in general it can depend on q and p or any number of operators, and the formula will still hold. And you can work that out by going to explicit energy representation and working it out. So I'm assuming that people again has at least a noding familiarity with it. If not, take this as the definition. So there is a way of constructing this density matrix and then working this out. Now, if you look at the structure of this and you compare it with the kernel we wrote down, which is somewhere here. Let's look at this. Yeah, here. The Euclidean kernel we wrote down. I mean, you find that they are identical. Okay? So the formula here is essentially the same as that, with t replaced by beta. Okay? So I can think of this density matrix rho of q prime as just the kernel to go to q at time beta, time quote unquote, time beta, starting from q prime at 0. This is the Euclidean kernel. Now already you can see something interesting is going to happen, because the Euclidean kernel in some limit is supposed to give you the ground state amplitude, and the same Euclidean kernel in some other limit is supposed to give you a thermal density matrix. And this is behind this identification that the ground state in an inertial frame is going to look like a thermal state for an accelerated observer. So I am slowly building towards that. So this is again a standard result in StatMech, and you can do this path integral and compute that. In particular, if you are only interested in the diagonal elements of the density matrix, when q prime is equal to q, you are talking about a system where this q prime and q are identified. So you are talking about trajectories if you think of evaluating it using an Euclidean path integral. Because just as this kernel has the standard path integral expression, this can also be thought of as sum over paths of exponential minus a Euclidean. So the action is continued into the Euclidean sector, and you are doing the sum in the Euclidean space. And if you are interested in the diagonal element, you are identifying the initial and final points, which means you are looking at paths which are periodic in the imaginary time. So if a path or a phenomena turns out to be periodic in imaginary time with a period beta, that is equivalent to having a temperature which is 1 upon beta. Okay, and there is a much more sophisticated way of proving this result, but essentially this is what is going to come up. Okay, so now we have the density matrix and we have the ground state, both obtained from the kernel. And again, everything which I have said here with just 1 degree of freedom Q carries over to a field. You can think of a quantum field Q of x and work the whole thing out. You can put that quantum field at a finite temperature, and you can do thermal averages of the field as well as the quantum mechanical averages, and all of them will be handled by this density. That is basically all the background information which we need. And with this, I should be able to show to you a very beautiful and elegant result that the inertial vacuum will appear as a thermal state to an accelerated object. In fact, the result is very general. It doesn't require to be an inertial enrender. For a wide class of spacetimes where there exists what is known as a bifurcation horizon, this result holds true. So I will use the prototype of the Rendler frame in order to illustrate the concept, and then I will tell you where the generalization occurs. So let us do that. There are many ways of deriving this, and what I am going to finally do in full is a derivation due to T.D. Lee. He just wrote 2 papers in this subject, as far as I know, and one of them contained this gem of a derivation. It's extremely beautiful and is very elegant. But in order to appreciate its beauty and elegance, I will first take you through a not so elegant derivation, but which is much more nitty-gritty in the sense that you can see what is happening, but I will not complete the algebra on that. But I will indicate how that happened, and then I will go back to this T.D. Lee's derivation and work that out. So the way it works is the following. Let us first recall a few results from this Rendler frame to inertial frame which we did last time. What we said was that if you start with a metric in flat spacetime, and let us do 1 plus 1, because we will make everything simple first, and then the T.D. Lee's derivation does not involve any of these assumptions, so it can be generalized. So if I look at 1 plus 1 metric, I have ds square, which is minus dt square plus dx square, and I pointed out that this can be transformed into the accelerated frame to have a metric of the form, let us say kappa square x square dt square plus dx square. If I stick to the right hand wedge of this spacetime, then the transformations which I needed to do this was t was equal to x sin h of kappa t, and x was equal to small x cos h of kappa t. Okay, so let us draw a picture. So what we have is a standard spacetime with Cartesian coordinates, x here and t here, and we had this 45-degree line which divides it into 4 regions, and we are thinking of an accelerated observer in this regime, and we are introducing a coordinate system which covers this regime and this regime for the moment. We are not worried about these 2 regimes. In particular, the coordinate system which we have will cover this entire t is equal to 0 prime, and the equations which I have written down here will take care of that, and with a flip in the sign of x, it will take care of this side as well. So the lines of constant x will go like this. This is x is equal to constant, and the lines of constant t will go like this. This is t is equal to constant. And we also saw, this is all done in the first lecture, that when t goes from minus infinity to plus infinity, you just cover this region and your horizon is here. This is the future horizon. And this corresponds to t is equal to minus infinity, and this corresponds to t is equal to plus infinity. Okay? So this is the coordinate system which we have in mind. Now I am interested in looking at the same thing, the quantum field theory for example, on both these coordinate systems. Since I am going to do 1 plus 1, it is slightly better to use the different coordinates compared to this, which also we derived in the previous lecture, where I will write this as e to the 2 kappa, let us say x bar, minus dt square plus dx bar square. The transformation is trivial. You think of this kappa x as e to the 2 kappa x bar, and that will take care of this because you have e to the kappa x dx bar is equal to this. Okay. So this is just one transformation there. So this x will become e to the kappa x bar, same here. So that is just instead of x I am using e to the kappa x bar. And you can use a similar set of coordinate systems on the left side as well. In order to illustrate that explicitly, I will put an R here, which means these are the coordinates on the right edge, and the x bar going to minus infinity is this point, and x bar going to plus infinity is this point. Similarly, I have a x left, which goes from minus infinity to plus infinity here. Okay. So I have two sets of coordinates covering this patch and this patch. The reason I wrote it in this particular form is the following. Now we want to do a quantum field theory of a scalar field, let us say, and the scalar field has an action which has to be now written in a generally covariant manner. So the massless scalar field in 1 plus 1 has the form, this is d2x, and in order to make it covariant, I had to put a root minus g, gab, dA of phi, dB of phi. As I said, I am simplifying things as much as possible just to get the essence. Now, since everyone has done a first course in general relativity, you will understand this. Root minus g is a measure for this integration, and you have to rise and lower using GA. Okay? Now, the interesting thing is, for a metric which is conformally flat, root minus g GAB is just eta AB. That is easy to verify because there is only one factor omega square here, so that will pick up one factor here, and this rising will give you exactly the reverse of that. This is just saying that two-dimensional field theories are conformally invariant, and this is conformally flat. So if I look at conformally flat coordinate systems, you end up getting the same wave equation as before. So the solutions to these field equations in either these coordinates or these coordinates are simply plane waves. Okay? So I can do everything which I am familiar with, like expanding in terms of harmonic oscillators, etc., using these coordinates. Except that these are different sets of harmonic oscillators. To make that very, very explicit, let us look at this field. Let us take this field phi on the t is equal to 0 surface. So I have phi, which is a function of capital X, which I am going to write as integral minus infinity to plus infinity dk over 2 pi. This is all in inertial coordinates. Some q of capital K e to the I kx. Just a one-dimensional Fourier transform. Okay. Now I can write the same thing both on the right side and left side, using this x bar right and x bar left. So it is most obvious if I try to write a reverse mapping for this. From this I will have qk coming out to be integral minus infinity to plus infinity dx of phi of x e to the minus ikx. This is standard inverse Fourier transform. But in this integral, the phi of x, the dx integral I am now going to split from minus infinity to 0 and 0 to infinity. So when I do in minus infinity to 0, I can also write it as integral minus infinity to 0 dx e to the minus ikx. I can write this phi of x there as integral minus infinity to plus infinity dk left, lowercase k left, 2 pi. Let me call those modes as some bk's. bk e to the I k left x bar on the left plus a similar integral which is 0 to infinity dx e to the minus ikx ikx integral minus infinity plus infinity dk right upon 2 pi. Let me call those coefficients as ak e to the I kr xr. This might look like a mathematical jugglery, but it contains important physics. So you had the degrees of freedom, the harmonic oscillator degrees of freedom, defined in the inertial frame in terms of this field by this relation. This is a standard relation. So these are the harmonic oscillator degrees of freedom. I would have constructed the ground state wave functional, for example, by taking e to the minus half omega these qk squares. I want to express these degrees of freedom in terms of the degrees of freedom which a Rindler observer will use. So for a Rindler observer, we are looking at this t is equal to 0, and the entire t is equal to 0 is covered by this q capital K of the inertial observer. But the Rindler observer uses a different coordinate system here and here, and here he uses a set of modes which I am calling AK, and here he is using a set of modes which I am calling BK. Alright? So in that integral there is a minus infinity 0 dx this much, and for this qk which I have to write down there, that phi of x at negative values of x, I am doing a Fourier transform with bk e to the I kl xl dkl. Then here I am going to use dkr and write it like this. Therefore, if I combine that together, I get the result that q, this k, can be written as, let us look at this first one. There is a dx integration over this, and I know what is the relationship between capital X and this xl. It's a horrible relationship because it is given by that sin hs and cos hs, but in principle it can be written down. So I have an integral over this, which let us say gives me some function. So I can write this as integral over dkl over 2 pi minus infinity plus infinity. In fact, now I can think of it as generically some quantity. Let us say some function which depends on KL and capital K which is obtained by integrating this dx, this and this. This and this integral together gives me that, times b of kl, which is this. Then I get a similar integral on that side, which I will just call g of, say, okay, I decided not to use this, yeah, g of k, comma k, Now you can explicitly work out those integrals. As I said, this is the horrendously complicated way of deriving things, so I am not going to do that. But I just want to indicate to you that the q now becomes a linear function of bk and dk. Okay? And that is what is going to make all the difference. So originally I had a set of variables, and this is now going to look as a linear combination of two sets of variables, one on the left side and the one on the right side. Okay, now let us go and look at the vacuum state. This is all the maths which we need. We now look at the vacuum states in the inertial frame at t is equal to 0, which we know is given by some functional, which is, except for some normalization constant that I will just generically denote as n, it is exponential minus half integral over dk over 2 pi. We wrote it down a little while ago for d dimensions. Then the massless field, so the omega k is just modulus of k, qk square. This is the vacuum state, and in this we are going to substitute for this qk, or rather we should, I am not going to, we have to substitute for that qk this expression. So the qk is going to be a linear sum of these quantities, and you work that out. You take mod qk square, these functions are known, these are given as integrals, and you can compute it. But the generic structure, when you do that, since it is a quadratic expression, you can see that this is going to go into an expression of the following form. You will have exponential minus some half integral over some dk over 2 pi times, the expression will turn out to be, let me just use some symbols, some a of k, script a of k, times ak square plus bk square. They will certainly exist. Then you will get some other coefficient b of k times some ak bk star plus ak star bk. I don't want you to get lost in the maths. What we have done is that we had one scalar field at t is equal to 0. We Fourier transformed into qk. Then we said I am going to also Fourier transform it in terms of ak's and bk's on the left and the right. Then we found a relationship between qk and ak and bk and expressed the ground state wave functional, which was a quadratic in qk square, in terms of the new wave. What we find is that this is not a ground state wave functional in terms of ak's and bk's. That is obvious. Because if it has been a ground state wave functional, this a of k should have been just k, and this term should be absent. So a ground state in terms of one set of variables does not look like a ground state in another set of variables. Yeah, there was a question there.
Yeah, in what sense there is more reality in the Fourier modes? In why our variables are the q, k, and not the fields?
No.
How do you know that?
You can do the whole thing completely using the fields, And in fact, the TD-Lee's derivation, which I am going to repeat, will not introduce any Fourier modes. The Fourier modes here are done just for convenience because you have some intuition on holes about harmonic oscillators. So each of these modes are quadratic in the harmonic oscillator modes. So for free field theory in 1+1, it is just to bring upon that intuition which we have about harmonic oscillators that I am using this. It's completely not necessary. And in fact, I would agree with you that the fields are more real than the Fourier modes. And we will do it with you. Okay? But the key point here is that the ground state now looks like this. But that is not the end of the story. So the ground state now has both AKs and BKs. Right? But suppose somebody is going to observe something just on the right verge. So we have this observer who is sitting here. And he will construct some observable here on the right verge, which depends only on, let us say, his variables AK. Okay? And he wants to look at the quantum theory of that. In particular, he may want to compute its expectation value. What will he get? What he will get is something like this. He is going to evaluate the expectation value of this quantity, which is going to be integral over d of AK, d of BK, the wave function which we have written down here, psi of AK, BK, psi star of AK, BK, this is just getting the modulus, times this operator, which I would now stress depends only on AK. This is how he will do that. He is just calculating the expectation value. He takes that observable, takes the mod square of the thing and integrates over all the variables. Now since this depends only on AK, you have a free integration over dBk. So you can first of all do that integration once and for all and define again a density matrix, which I will call AK prime, which is defined to be integral over dBk of this ground state wave functional, which is AK BK psi AK prime BK. So I now here has a psi of AK BK. This is what I call A comma B, let us say. It depends on this whole set of variables. From that I can construct this rho A prime by just integrating out the degrees of freedom BK. That makes physical sense. So I have a vacuum functional which depends on variables on the right verge and on the left verge. As far as an observer who is sitting in the right verge is concerned, he doesn't care what happens at the left verge. So for calculating probabilities, he will just integrate out the degrees of freedom which are not observed. This is what we will do in statistical mechanics. The degrees of freedom which are not observed are integrated out. So you integrate out this BK. What you get is the incomplete description of the system is in terms of a density matrix. Then this expectation value again is our old friend. It is trace of rho O. Because now if I put A is equal to A prime and then integrate over that, that is precisely what I get. Right? So you had this vacuum function, you wrote it in terms of AK and BK. I said I don't care what BKs are, thereby getting this density matrix, and that density matrix allows me to compute any expectation value. So what you need to do is to take this expression. I haven't even told you what AK and BK are. That happens to be hyperbolic cotangent and hyperbolic cosine. It is done in the notes. You take that expression, then you do this integral. This is a Gaussian integral, so they are doable. When you do that, you find that this density matrix happens to be precisely thermal, the thermal density matrix, with the temperature. When you do this computation, you will find in this case that rho is just exponential minus beta h, with beta equal to kappa over 2. Beta inverse equal to kappa over 2. Okay? Now, until you do that computation, there is no inkling whatsoever, until I can't see it and anyone I have talked to couldn't see it, as to why it is done. That is why the derivation I am going to give, maybe after the coffee break, of the TD list is so transparent. It clearly tells you where it comes from. Okay, I'll do that. But this is the nitty-gritty way of doing the calculation. You take the vacuum functional, express it in terms of the 2 modes, integrate out the modes which you don't observe, and see what it is. Whatever you get is what the physics demands. And it turns out to be a thermal row of this kind. Okay? Now, yeah, you have a question?
So can you do the whole thing also the other way around, kind of set up the ground state for all observers in the Rindler frame and see what kind of the...
Oh, okay, so you're saying what the Rindler vacuum will look to a Minkowski guy. It looks horrendous. It is not anything which has a simple physical meaning for several reasons. First of all, the Rindler vacuum is not a complete state in the manifold. Okay? So when an inertial, all that you can ask is that if I have a inertial guy moving through that part of the space, suppose you set up the inertial vacuum here, the Rindler vacuum here, and then you say that there is an observer who is just sitting here. Between these two horizon crossing, what does he detect there? That question can be asked. Okay? And that response function can be worked out. This has been done in literature, but it is nothing simple. So there is no symmetry across the two, and you don't expect any symmetry because this is accelerated frame, so it is not like 2 inertial frames or some such thing, and it doesn't come up. But before we break for tea, I just want to make one point about that final result. I told you the other day, without much motivation, that if you look at this metric, and you analytically continue from T to TE, then this becomes plus, and kappa TE you think of as theta. Then this is dr square plus r square d theta square. Right? And if you don't want a conical singularity at the origin, that theta should have a period 2 pi. That means kappa TE should have a period 2 pi, TE should have a period kappa over 2 pi. But that is precisely what we found earlier. That if the imaginary time has a periodicity, that period, as far as mathematics goes, which doesn't care where it came from, it is identical to working with a density matrix, which is thermal, with a beta related to that period. So one simple way of seeing the whole result, if you believe that, is to just look at it and say, aha, it has a periodicity in the imaginary time. Because it has a periodicity in the imaginary time, the temperature has to be kappa over 2 pi. Now you can do all kinds of maths, but finally that is what you should get, and that is indeed what you get. So that is a very quick way of saying this, but I will try to do this a little bit more formally, using only the field modes, and try to obtain how to get this thing. So I think this is logically a good place to stop, even though there are 15 more minutes, and then shall we come back at 4? Yeah. This derivation, as I told you, is algebraically complicated because it involves you to evaluate these integrals, put this back into this AK and BK, and then do one more integral here to obtain this result. So in the process, you lose track as to the elegance of the result, and you don't understand why this is happening. So I'm going to redo this in full by a completely different method, which will also address the question you raised, that it will not use the Fourier coefficients. It also doesn't require much of the paraphernalia of a free field theory or this explicit form of this Gaussian wave functional, etc. So in that sense, it is quite nice. So let me do that next. I think I have this picture here, so let me do that and connect it up. First of all, I want you to recall from the previous lecture that this kind of transformations and this diagram is very generic. That for a wide class of spacetimes which had FFR dt square minus dr square upon FFR kind of systems, I showed you that this kind of Rindler transformation, Rindler-like transformations arise very naturally. So all that I am planning to use is the fact that there is a t is equal to 0 plane which is mapped to a small lowercase t is equal to 0 plane under a coordinate transformation. And second, the metric is periodic in this lowercase t. Just to emphasize that point, let us write down these expressions explicitly in terms of the Euclidean time. So you have Te, which is x sine kappa Te, and capital X equals x cos kappa T. This analytic continuation introduces a new element into the picture. Suppose you look at these coordinate transformations and I let t go over the allowed range, which is minus infinity to plus infinity. At no stage will I get negative values for capital X. Let's assume this small x is positive. Keep small x to be greater than 0 and let t go from minus infinity to plus infinity. This function always remains positive because it's a cosine function. So I'm never going to get negative values of x. What it means is that when I have a hyperbola like this at some constant x, as I run t going from minus infinity to plus infinity, you keep getting curves like this, but I never cross over to the horizon. Makes quite a good of physics sense because these are the accelerated observers. They don't see this. But look at what is happening in the imaginary time. In the imaginary time, when I let this Te go from minus infinity to plus infinity, it keeps winding round and round towards. In particular, the moment kappa Te crosses to pi by 2, it is going from this half to this. So let me draw that in a pictorial form. So now what we are having is the same picture, capital X, but in Euclidean time. This is Euclidean time Te, and your small x is like this, and this anchored is kappa T. So when kappa T crosses over to this side, the values which you are going to get will have negative values of x. What it means is that the imaginary time has information on what is going on beyond the horizon, with the real time doesn't have. And that is the crucial point, and that is how all of these phenomena, which has to do with the degrees of freedom which is hidden by the horizon, becomes apparent when you go to the analytic continuation. And that is what we want to see. So I am just going to have this minimal apparatus that there exists some coordinate system where the time is periodic, the imaginary time is periodic in the Rindler-like coordinate system, and you can go from here to here with that period. And this is an x is equal to 0 which maps to t is equal to 0. Given this much, I will first prove for you a result that if I take the vacuum state of the system, let us say the ground state, which I will call vac, and write it in terms of some field variables. Let me just call it Q, which of course is, for a moment I will denote it in full, it is the functional, and in fact it is a functional on inertial coordinates, so let me put a capital X here. This is all at t is equal to 0 on that horizontal line. This can also be written as vac in a representation where I give you the coordinates on this side and coordinates on this side, which I can call, let us say, b of x and a of x. So now I am not using Fourier variables. nothing fancy here. You are given a vacuum state in functional representation, and that can be expressed either in terms of a functional q of x, which is all over this x-axis, or it can be given in terms of q of x for negative values and q of x for the positive values. Q of x for negative values I call b of x, positive values I am calling as a of x. So here is your b of x, and here is your a of x on this, and q covers the whole thing. What I will show is that this can be written as proportional to b e to the minus pi over kappa, not 2 pi, pi over kappa h a. Okay, where h is the Hamiltonian as seen by the Riddler result, which allows for the system to evolve forward in Riddler time, just as the normal Hamiltonian will evolve forward in inertial time. Once you have that, the normalization is trivial. You can just normalize it fairly easily. And once you normalize that, and if you compute expectation value of any observer on the right hand side, it will turn out that they are thermal expectation values. So the key thing is to first prove this result, okay, which I will do. So where does that come from? Maybe I can, yeah, I need that picture too, so let me see. Yeah, I can rub the top part of it. Okay, let me just rub this part. So what I need is an expression for this, and this is a vacuum state. Therefore, I can write that vacuum state vac q of x as a kernel is all proportional because normalizations are not taken care of yet, as proportional to the kernel, which I can think of as starting from something and going up to infinity. So I'll put infinity, let me make it absolutely clear by saying t e equals infinity, 0, t e equals 0, q. This we proved earlier on. We said that if we know the kernel and I take in the Euclidean time infinite laps in the time, and I set the functional on one of them. So this is essentially what we proved in one of the two representations using the kernel. That gives me the ground state wave functional in terms of q. So we know this. We also know that this is given by a path integral. This is sum over paths of exponential minus the action with the same boundary conditions as this. Okay? This way. Now what we want to look at is the same path integral slightly differently. This path integral says that you take q of x on this and you integrate this. The boundary condition, let me again write it down here. The boundary conditions are Te is equal to 0 and there is a field q and Te equals infinity and the field is 0. Okay, this is what we are doing. So this is phi is equal to q, the field is q, and here phi is equal to 0. Okay, so you start with the field here, and you are doing the path integral over these time slicing, all the way up to infinity, and this gives you this ground state wave function. But we know that if I am going to do the path integral on this upper plane, I could have used any coordinate system I like. This is the Cartesian coordinate system. This is just a two-dimensional plane with Cartesian to polar. I could have equally well used the polar coordinate system. If I had used the polar coordinate system, then the evolution here is going to be from here, like this, to this point. Therefore, the same quantity should be expressible as the sum over all paths, where the paths begin with TE equal to 0 and phi is equal to some A, and go to TE equal to pi with phi is equal to B times this exponential minus A, which of course is the kernel in the Rindler frame. So I'll call it kernel in the Rindler frame of T. This is kappa T is equal to pi. So TE is equal to kappa pi over kappa phi is equal to B, starting from T is equal to 0, phi equals 0. Essentially that is all I need, so let us stare at it. What has been done is the following. There is a Euclidean path integral evaluated all over here with a boundary condition on this surface. Now I can view this in two different ways. I can say that I give this boundary condition, then I go step by step, make sure that the boundary condition at infinity is 0 and I evaluate it in one way. Another way of doing the same thing is I do the whole thing in polar coordinates. I start with this and then I go like this. At every time I integrate all over here, making sure the thing is vanishing at infinity, and I go from A to B. This, of course, is nothing but, this is just an evolutionary kernel. So again it is proportional to B e to the minus time evolution, which is pi over kappa times whatever is the relevant Hamiltonian, which is H Rindler. End of story. So this is equal to this, which is this claim. That's all you need. Okay? So it is remarkably simple. Let us go a bit further with it, and then we will come back and ask what inputs have gone and what is the physics, etc. So what does it buy you? What it buys you is the following. We want to first normalize it. And then we will use it to calculate expectation values. So normalization involves a bit of algebra, so let me make sure I get it right. What we have is vac Q is, let us say, some constant C into B e to the minus pi over kappa H A. So this is normalized to unity. So I must have 1 equals C square. So I will ignore the phase in that C. C square. I have to take 2 copies of this and integrate over A and B. So I am going to have integral over dB, dA, B e to the minus pi over kappa H A, and since its ground state is real, I can reverse it and write this as A e to the minus pi over kappa H B. So the integral over dA will just introduce a complete set of states. Therefore, this is equal to C square integral over dB B. This just vanishes. So it becomes e to the minus 2 pi over kappa h B. But that is just your usual trace. So this is C square trace of e to the minus beta h. I will introduce the notation beta to identify 2 pi over kappa. So this is what we have. Therefore, the C here is just 1 over that quantity, and this can be written as B e to the minus pi over kappa h A divided by trace e to the minus beta h to the power half. So this is the expression for the vacuum state in terms of the Rundler modes. Okay? So obviously this is an extraordinarily elegant and economical way of getting the same expression, and this is what you would have done by all those integrals which I mentioned. Now given this, suppose I want to now compute the expectation value of some object which is just in the right root. So I can write this also as vac some b comma a instead of q. Q is just this set p comma a. Now I want to, I can do various things here. For example, I can just compute the density matrix and then say that it is a trace of that operator. So if I want to compute the density matrix, we have done this several times by now. So you want to do the density matrix rho, which is A prime which is obtained by integrating over dB of vac BA vac BA prime. Right? So this is the ground state expressed in terms of BA and BA prime. A is on the right and B is on the left. So we are just saying in order for calculating probabilities, you only need the mode psi square, which is just psi naught square, 2 copies of the same. And I don't care what is going on the left side. So I am integrating over D. So what is this? This is going to be, first I get the normalization factor, which is trace e to the minus beta h. That square root 2 factors will give me this. And then on the top I have to do this integral. So it is the integral over dB of, I can again write this as A e to the minus pi over kappa h B. So instead of this I am just reversing it. And then the next one I will write as it is B e to the minus pi over kappa h. Yes. So once again there is a complete set of states here which will just disappear, and you will get here A e to the minus 2 factors of them, that will give me beta h A prime divided by trace of this output. So this is a reduced density matrix with a trace equal to unity. This is what you do. So that's it. So it tells you that if I look at the vacuum state and I write it in terms of A and B on the left and right, and I compute the density matrix for A prime, the result which I get is just the matrix elements of e to the minus beta h. So as far as all physics on the right edge is concerned, the system will behave as though it is in a particular temperature beta inverse. Now what have we used for this, and why is this general? First of all, I never said anything about the particular nature of the Hamiltonian. So if you have an interacting field theory, some horrendously complicated field theory, it will go through for all of them. All that has been used is that there are two regions in space-time, and I didn't use any of the physics beyond t is equal to 0. Okay? What happens beyond t is equal to 0 is taken care of from the initial conditions through the Hamiltonian. So I only have to specify things at t is equal to 0. At t is equal to 0, I partition it into two sectors, the right and left, sort of arbitrarily. The only input which I need is that there exists a time coordinate in which there is a new Hamiltonian which is static, the HR, and the evolution in that time is same as rotating from the right to left, which is completely identical to imagining periodicity in the imaginary term. So essentially this puts the nitty-gritty on this loose statement that if I have a metric and the metric is periodic in the imaginary time, then there is a thermal behavior. Okay? That is too loose a statement, but if there is such a metric, then when you write down the proper coordinate system, you will be able to go from the right edge to the left edge by this angular rotation. And then by using the standard Path integral and the fact that the ground state wave functional is expressed in terms of this infinite time, quantity, etc., you end up getting this system. So I want you to understand all the ingredients which has gone in. First of all, we have used this fact between the kernel and the ground state wave function. Okay? Without that we couldn't have proceeded. And then we have used the relationship between kernel and the path integral, so that the path integral over the upper half plane can be computed in two different ways, which we have done. Then finally, we have also used the fact that when you have such a state, there is a natural density matrix which can be defined by this relation, which is also obvious, but it needs to be emphasized. This is, so to speak, we start with a pure state and we are just integrating out certain degrees of freedom. Now this analysis also makes very clear that the reason we are having some kind of a thermal behavior is because certain degrees of freedom are ignored. And that is what I like about it. There is this completely alternate derivations which can be provided for this phenomenon, which doesn't make this very clear. The existence of the horizon or what degrees of freedom is ignored, etc. But at least in this derivation, that is very clear. In fact, you can short circuit some of these steps. Now that we have done this, we can actually simplify this even further. And I want to show you how that comes about. And there is a way of directly getting the density matrix without going through even this vacuum state. So let me try to indicate that. Okay. To do that, what we will try to do is to start looking at this final expression and then see whether you can look at that as a evolution operator without going through the intermediate step. So what we are now interested in is to compute this quantity rho of A prime, which is defined as integral over dB of vac, I have written it down there, vac B comma A, vac B comma A prime. Right? Now these two vacuum states I want to represent using the kernel. So I will write it in the following way. I will say this is dB. The first state I will represent as a kernel in which I will take the integration from 0 to infinity. So the boundary conditions are going to be given here, and at infinity I set things to 0. So I am going to have t equals infinity, and the field vanishes. I will now put 2 zeros to say that the field vanishes both on the left and on the right. Starting from t equals 0, in which the field has the values, let us say b and a. This is the first one. This is multiplied by another kernel, in which I will do the integration from minus infinity to here. So I am going to have t equals 0, in which I am setting the fields to be b and a. And when t is equal to minus infinity, I am going to say that the fields vanish. Okay? Now the reason I write it like this is because now I have gone from t is equal to minus infinity, very much at the lower half, through t equals 0, then from t equals 0 to t equals plus infinity. So I have sort of covered this entire thing. Now I can write a path integral for this and a path integral for this. But it is a little non-trivial path integral, because even though the path integral has taken the field all the way from minus infinity to plus infinity, it is evaluated with a very specific boundary condition. Now what is the boundary condition? The first boundary condition is that on this surface, on the left I had b, and on the right when I was coming from here, from minus infinity, oh, I have forgotten to put a prime, sorry. This is a prime. The second one should be a prime. So when I come from minus infinity, I have a prime, and when I come from plus infinity, it is a. So let me again draw a picture to show that. So the boundary conditions we are imposing are like this. This is TE. This is x. And you are doing an integration from TE equals minus infinity to TE equals plus infinity. This is what we are doing. And when you integrate from here, here we are taking, when I am going from minus infinity, the second k factor, I am getting it to be a prime. And here, infinitesimally above this, I am setting it to be a, and here I am setting it to be b. Right? With these boundary conditions, I am doing the path integral all over the place. Now, the b I can completely ignore, because even though I set it to a value b, then I am integrating over b, which means that I am essentially not imposing any boundary condition here. All that I am doing is that there is a boundary condition on plus epsilon and minus epsilon on this. Here, I will use a trick to reduce this problem to something which is more familiar. What I will do is that I have to put these conditions on the lower half and an upper half on the t is equal to 0 surface, but instead I will do it as a limiting case of the following. What I will do is to take this small t and set it to epsilon, this angle is epsilon, and I will set it to another angle here which is also epsilon, so this is 2 pi minus epsilon, and then on this I will put the condition A, the field is A, and here I will put the condition t is equal to 2 pi minus epsilon, and I will set the condition A prime. In the limit when epsilon goes to 0, it reduces back to the previous boundary condition. Okay? So once I have done this integral, the b goes out and the kernel just goes from one end to the other, and what I am left with is essentially a path integral over the whole space with a boundary condition on this and a boundary condition on this, which is same as starting with a boundary condition like this, evolving this system in this time like this, and getting back here. Therefore, the same path integral kernel could have been written as k in the Riddler frame, starting from ending at Te equal to 2 pi kappa T is the angle, 2 pi minus epsilon with A prime as the variables, starting from kappa T equal to epsilon with A as the variable. In this, of course, there is no harm in taking the limit epsilon going to 0, so you just remove this and put this equal to 0. But this is just a propagation kernel, therefore this is proportional to, in fact this is proportional because I have not normalized things. This is proportional to A prime e to the minus 2 pi over kappa, that is the time interval, times the Rinder Hamiltonian, starting from. That's it. So the density matrix itself, which has elements A and A prime, is turning out to be the matrix elements of e to the minus 2 pi over kappa HR, that operator. So from which you can immediately identify that the density matrix rho is exponential minus our beta HR, proportional to, depending on how you normalize that density. So this derivation makes this a little bit more clearer, at least in my mind, that nothing on this B side is relevant. The path integral which you are computing in order to calculate the density matrix essentially goes around a full circle here. With at the epsilon above you give one boundary condition, and when it comes back you give another boundary condition. And that evolution is by 2 pi over kappa. And that is why the density matrix has this structure, and which is purely thermal. Okay? So this is, as I said, this derivation carries over to anything. If you start with some arbitrary space-time, which can be reduced to Rinder, then you can play the same game. This we have done in the last lecture, but just to remind you, the way it comes about in the case of a black hole space-time, etc., is the following. Let me just write it down. What we found was that a whole class of space-times has a metric which is of the form minus f of r dt square plus dr square by f of r plus some transverse coordinates which we don't care about. Then all these metrics has f vanishing at some point r is equal to a. So r is equal to a is the horizon. And the f prime evaluated at a you define as twice kappa. Then near that point, this reduces to minus 2 kappa L dt square plus dl square upon 2 kappa L plus dl square, dl perpendicular square, where your L is defined to be r minus a. Then we found that there is a further coordinate transformation which you can introduce, by which this can be written as kappa square x square dt square plus dx square. This is obvious, you just put this equal to this and this will take care of itself, plus dx square. Now if you reverse all these steps of transformation, you will find that the only property which we require is that in the final analysis, kappa times t is periodic with a period 2 pi, and that will be intact even in a curved spacetime. And using that result and the analysis which I have given you, you can show that all these spacetimes has a temperature beta inverse, which is kappa over 2. Okay?
Sorry.
So, yeah.
I mean, just to stress, here you're assuming that there is a vacuum which is defined
Globally on the...
globally
Yeah,
defined.
that's correct. That's correct.
Because
So-
for example, you could imagine changing the state in the other part of the relay horizon.
The part which is not observed? Or
Yeah,
the...
and everything would be like a mess.
Okay, that is an interesting point. Okay, so let me make two comments. First, the point which he was saying, which I should stress, is that the claim is a vacuum state in the global capital T equals 0 prime looks like a thermal state to observers who are confined to the Rindler world. This is the theorem which has been proved. Now the question is, suppose it is not a vacuum state. Suppose you have a state which has some vacuum-like behavior, let us say on the right wedge, but the field configuration is completely different on the other wedge. Okay? Then when you repeat the calculation, you will get some other kind of a density matrix. That is because there are correlations across the quantum correlations across the horizon, which you cannot ignore. And when you compute it, it may not even be a thermal state. So in general, all bets are off. But the statement is only for this vacuum state. But for anything else, you can do the computation along the same line, because you can write down that waveform and you can compute it. Okay. So this identifies in a particular way how to get this temperature for, yeah, sorry.
So I have another question that's maybe a bit silly now. So here in the Rindler case, we have basically the global state has like 0 temperature, nothing there. And
Well, at least that is what we hope, yeah.
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 Okay.
Yeah.
And then the Rindler observer sees
Okay.
the temperature. Now in the black hole case, the observer outside sees the temperature. So is there an observer that sees a zero?
Okay.
Zero
No,
temperature state?
I'm coming to that. Because there is a slight difference between the temperature attributed to a black hole spacetime because of Hawking evaporation and the temperature we have been deriving so far. The temperature we have been deriving so far does not have any flux. In the Rindler frame, there is no flux of radiation. This is like a thermal equilibrium state. And the technical term is that this is what is known as a Hartle-Hawking vacuum state in the black hole spacetime, where there is a temperature, it is like an eternal black hole, and there is nothing which is collapsing and forming the black hole, etc., so there is no flux. But the reason you get a flux from a collapsing black hole is slightly different. I'm going to do that.
But so there you would have to set up an external radiation.
That's
field
correct.
on-
That is correct. There is a vacuum state which has to be defined for the in modes at very early time. They will appear to be a different kinds of modes at late time. I'm going to do that explicitly in a minute. Okay. And, then we will come back to that. So this is only as far as the static spacetime is concerned. I'm just trying to describe to you how this comes about. And there is also another reason for that, because some of you might go and read textbooks, not only the books written by me, and then you need to be able to translate these results into the conventional language. In the conventional language, these are obtained by a method known as Bogoliubov transformation, which is what is also used in condensed matter. But I just want to briefly introduce where that comes from. It comes from the following fact. Take Rindler again. In the Rindler, I know that you can write down the metric like this, which also goes into minus dt square, dt capital T square plus dx square, right? The interesting thing there is that, suppose I, just to complete, let me write that, dt square plus dx square plus dl perpendicular square. Now you find that something interesting is going on here. Both these metrics are static. Both these metrics, the metric coefficients are independent of their own time coordinate. This small t does not appear in the metric here, capital T does not appear in the metric here. Therefore, I could have done field theory in which I expand a field. Let us say you take a field phi, which is a geometric coordinate independent entity, and I could have expanded it as some e to the minus I omega capital T times some function which depends on omega and the spatial coordinates in the inertial frame. And I could have also expanded it as e to the minus I small omega t, some other function g omega, which depends on the Rendler coordinates. I could have taken the equation which is satisfied by this phi, let's say box phi is equal to 0, and I could have done either one of these. And then the spatial parts will determine what these functions are. And I can define complete set of functions, etc., etc. But obviously the relationship between capital T and small t is horrendously complicated. It's not a linear function. Therefore, if I take these modes are called the positive frequency modes because they go as e to the minus I omega with omega greater than 0. These positive frequency modes will be a mix of positive and negative frequency modes when I write it in terms of the other. This in turn, in the conventional field theory, you introduce a creation and annihilation operator. If you are working in flat space-time, for example, I would have written phi of t comma x, which I would have written as some integral over, let us say, t3k with some normalization constants times ak e to the ikx plus its Hermitian conjugate, which is ak dagger e to the minus ikx. Right? This ak and ak dagger are the annihilation and creation operators for that particular mode k. What it tells you is that I could have equally well done this using Rendler time rather than the coordinate time. And then if you look at the relationship between the Rendler annihilation and creation operators, they are linear combinations of the inertial annihilation and creation operators. So in particular, if you look at A dagger A, which is the number operator in the Rendler frame, it is going to be a mix of the quadratic variance of the A's and A daggers of the other frame. As a result of which, when you calculate the vacuum expectation value of A dagger A, the A dagger A is, they don't completely annihilate this vacuum and you end up getting a residue. So this is the way it is conventionally done, and that uses this fact that the positive frequency modes depend on the time coordinate which you are going to choose. Okay? I somehow find the other method much more appealing because it geometrically tells you that the vacuum has field fluctuation, and these fluctuations sort of change in a particular way when you block out certain regions in space-time, but they are mathematically, both these are equivalent. The reason this whole thing works is because I could write down a metric which either t as a static coordinate or t as a static coordinate. This has a fundamental reason. This has to do with the fact that if you are in flat space-time, it has tremendous amount of symmetries. It has the Lorentz symmetry, which has 10 generators, the 4 translational generators and the 6 Lorentz loop generators. In particular, if you take the Lorentz boost along the Tx plane, there is a killing vector associated with that. And that killing vector, the integral curve to those killing vectors are the hyperbolas which we have been drawn. Okay? So if you move along that hyperbola, it will look as though nothing is changing with time because we are moving along a killing vector field. And that killing vector is just the Lorentz boost killing vector of this space. That in component notation, in this I would have written down there is a killing vector psi I in the Rendler frame, which is 1, 0. In the inertial frame also there is a similar one, and if you transform this to the inertial frame, you will find that this actually corresponds to the Lorentz boost along the Tx plane. So it is that Lorentz invariance which is appearing here as some non-trivial dynamical evolution. Okay? So this is the root cause for this 2 static coordinate systems and 2 static time coordinates to exist. Taking out of that, you can ask a more general question. I said that there are 10 linearly independent killing vector fields in flat space-time. Take linear combinations of them and arrange matters in such a way that in a particular region that vector is time-like. Draw the integral curves to those vector fields and put an observer on that. Any such observer will see things to be static. So there is a whole class of observers for whom the quantum field theory will not show time evolution in the new coordinates. But not all of them will exhibit thermal behavior. That is because some of them will not even have horizons. So this has been worked out in literature. So just having the static nature is not good enough. You need that plus this horizon which blocks the degrees of freedom. Okay, that is how this result comes in. Now I want to switch gears and take up another topic, which is the actual emission of radiation in the case of a black hole. And this is coming back to your question. Yeah.
Can it be proved that for any choice of observer that is a horizon, then you have a thermal or
okay. You can do the following. I mean, there are horizons and horizons in literature. There is a particular class of horizons called bifurcation horizons. You can prove that if there is a bifurcation horizon, then all the statements which I made are true. There is a thermal behavior. But for a more general class of horizons, I don't know of any proof. It may not exist.
One get a density matrix, say.
Yeah, you can certainly write down a density matrix, but the question is whether it is a thermal and whether it's a globally well-defined state and things like that. But for a bifurcation horizon, it works out fine. And the reason people have not spent too much time looking at it is because virtually every horizon which we are interested in seems to fall into this category, which is close to the horizon, it is Rindler, and all these nice properties hold. Okay. So now I want to look at a question which is slightly different, which is if I have some matter which actually collapses to form a black hole, what kind of phenomena takes place around it? One might have thought that the temperature which I have obtained is good enough to just tell you that it is going to radiate, etc., etc. But a moment of thought will tell you, show you that that is not really true. There is a fundamental difference between these two cases. If you have matter which is collapsing and forming a black hole, it is a time irreversible process. While if you have an eternal black hole, that is if you just look at Schwarzschild metric as a vacuum solution to Einstein's equation with a Kruskal extension, etc., etc., that is a completely time symmetric situation. So in a time symmetric situation, you can have thermal equilibrium and a temperature, which if you want to, you can think of it as a flux of radiation going in and an equal component of flux of radiation coming out of the horizon and everything being in balance, which is somewhat similar to what is happening in the Rindler case. But in a time-dependent situation, you have a flux only in one direction. So the result in that case is the following. If you have matter which is collapsing to form a black hole, and you have an observer who is outside, at very late times, he will see a flux of radiation. It is almost like you getting light from the sun. You will see a flux of radiation flowing towards infinity, and that radiation will have a Planckian spectrum with a temperature which happens to be kappa over 2 pi, which is identical to this result which we have obtained. So I want to derive that. Now again, the actual derivation, the details of the derivation is given in the course notes, so I won't go through too much of the details of that. But I want to first illustrate something there, which is useful and which will tell you something interesting which is happening. In order to do that, I want to generalize the Rindler frame to the case of a time-dependent acceleration. That is what we are going to talk now, is that you have an observer who is moving in inertial frame with an equation which is the acceleration equals some g of t. Okay. Now it turns out that you can integrate this because you can just give g of t is given, so first integral is done and then you can do the whole calculation. Then you can write down the coordinate system which is suitable for this observer. You can do this entire thing which we have done for the Rindler observer. And the final result is that you will find a metric for this observer, the line element, which has the following form. Is again remarkably simple. It is 1 plus g of t x the whole square dt square plus dx square plus dy square plus dz square, etc. So this is amazing. If g was a constant, we know that this is the metric. This one doesn't matter because I can just scale it away. If g is a constant, by just shifting x by x plus 1 over g, this is just g square x square. G is what we have been calling kappa. Okay, so kappa square x square dt square plus dx square. Now it turns out that when g is time dependent, you just stick in that time dependent inside it and it works. Okay, so it's very nice. What we can do now is we can now think of g of t, which starts at 0. So we can say that the observer is not accelerating all the way up to, let's say, t is equal to 0. So it's completely static. And then he starts accelerating. And then much later on, he may even go uniformly accelerating. So you are thinking of a trajectory, for example, like this. You have the x and t, and you have an, let us say, a 45-degree line. You are thinking of an observer who is like this, for example. So he is at rest up to t is equal to 0, and then he sort of goes into a uniform accelerated trajectory with a small transition time, and asymptotically he is just going like this. What would he see? Suppose you are in an inertial vacuum, and what would he see? This is a time-dependent phenomenon. I mean, there is no static coordinate system, and the second coordinate system explicitly depends on the metric, etc. Okay? So you need to work this out. This can be done. So I'll just indicate to you how this happens. So if you take a scalar field, phi, let us take a scalar field phi which depends on t and x, and you expand this into modes which depends on f of t comma x times the transverse coordinates, which is exponential I, some k perpendicular dot x perpendicular. So if we are talking about 3 dimensions, this is y and z. So you put in this sort of thing, and you can separate variables on the transverse directions, and you can write down the differential equation which is satisfied by this f. And that has a solution which I will just write down. This f of t comma x, you can write down the field equation and then solve that. And when you solve it, you get a solution which is of the following form. Some constant exponential minus I, some capital M, which is a constant, integral dt cos h of chi minus eta plus x sin h of chi minus eta. Okay, let me define the various quantities. The m square is essentially m square plus k transverse square is like the effective mass in the xy plane, and the chi is related to the acceleration g of t by d chi by dt. So chi is just the integral of the acceleration. This defines your chi, and eta is just another constant. Okay, so let us again stare at it to see what is going on. What I said was, I have an observer who is on a variable acceleration track. So he has a metric which is like this, and he is doing quantum field theory. So this time I have switched back to the standard conventional Heisenberg picture quantum field theory. So the quantum field satisfies an equation box f plus m square phi is equal to 0. You can separate out the transverse degrees of freedom, then you get a differential equation for this. Fortunately, given the simplicity of the problem, this equation can be exactly solved, and the solution you get is this. Okay? Now we want to stare at this equation as solution and see how it behaves asymptotically. So there are two limits which one is interested in. First limit is when you go to t is equal to minus infinity, when this chi actually vanishes. Okay? When chi vanishes, that is your acceleration is 0, and we will take chi also to be 0. So you have a cos h of eta and a sin h of eta. So this is just a linear combination. So what you get is that this goes as t goes to minus infinity, or even t less than 0 if that is the trajectory, to n exponential minus I. It is going to be m into some t cos h of theta plus x sin h of eta. These are just your standard plane wave modes. Because I can just define m cos h of eta as omega and this as kappa, and then you just have a e to the I omega t minus kx kind of a thing with proper sign choices. Okay? So this is just your standard plane wave modes you are starting with. So you can define your vacuum state using these modes very early. Now you want to ask what is going to happen at very late times. At very late times, let us assume that g goes to a constant, so that the chi goes to gt. Okay? So I am going to assume here that with g goes to 0 as sufficiently fast as t goes to minus infinity, and this goes to some constant, let me call that kappa, as t goes to infinity. So that means your chi goes to 0 as t goes to minus infinity, and chi goes to some kappa t as t goes to infinity. So if chi is kappa t and t is very large, then only the exponentials will survive here. And let us see what this gives rise to. As t goes to plus infinity, let us look at that behavior. This is n exponential minus im integral over dt cos h of, there is a constant, okay, let me write it in full. So it is cos h will become just exponential with a factor half, exponential chi is gt minus eta. This is what the first factor gives, plus x by 2 exponential, this is also gt minus eta. Okay. Now this integral of course is trivial to do, so this is just going to give me an 1 over g here. Oh, this is kappa. We said it goes into kappa, so it is 1 over kappa. And this is kappa. Alright? So this can be written as n exponential minus im by 2, taken this 2 out, then I have an exponential kappa t minus eta e to the kappa t minus eta into, everything is taken care of here except this kappa, so let me keep that kappa outside, 1 plus kappa x. This is a strange result. What we have found is that we solved the quantum field theory problem completely, and we found that when we start with modes which are nice plane waves at t is equal to minus infinity, and we evolve it forward in time, at late times the modes has a time dependence which is an exponential of kappa t. Okay. Last time we saw an exponential red shift, this is a blue shift, but that doesn't, either red, blue or red, it doesn't really matter, but it's an exponential dependence in time. So an observer who is at constant x, for example, will see this wave field as though it has an exponential of an exponential time dependence. So this is not a monochromatic wave at all. So you started with a monochromatic wave with just positive frequencies, and at late times it has evolved into a wave which has a very complicated time dependent frequency. So what you can do now is that at late times, what are my natural modes? At late times, what does the metric become? The metric at late time goes over to just minus 1 plus kappa x square dt square plus etc. So the most natural modes I would think of at late times would be something like 1 plus kappa x t as my proper time coordinate, and it should go as e to the minus I omega that time. So this is just a scaling factor, so you can think of it as e to the minus I omega times t, small t, rather than like this. So I can think of this as expressed in the form integral 0 to infinity, let us say d nu of some alpha nu e to the minus I nu t plus beta nu e to the plus I nu t. Right, where alpha and beta will depend on all other variables. So what was originally a purely positive frequency mode in time has now become a superposition of positive and negative frequency mode. And if I now do quantum field theory again, it is equivalent to mixing up my creation and annihilation operators. I originally start with a creation operator and an annihilation operator. They will now be a linear combination of alpha and beta, and the superposition between the positive frequency mode and negative frequency mode, which is given by this beta, modulus of that, modulus square of that, will tell you how many particles I will see in this vacuum state. So if I had started with a vacuum state and I accelerated through that, at very late times, I will see that this accelerated, this vacuum state is populated with particles. And we had already seen that if you start with an exponential of an exponential and you do its power spectrum, this we did in the first lecture itself, then you get a Planck spectrum. And the only thing which matters is this exponential kappa, and this kappa over 2 pi is the what gives you the temperature of the Planck spectrum. This is precisely what happens in the case of a black hole spacetime. As I said, this is a warm-up for the black hole spacetime. Now let me tell you how this comes about in the black hole spacetime. Again, as I said, I won't work out the mathematics, but let me try to indicate that. What happens is the following. So let us think of a collapsing structure, and since the result is completely independent of what kind of collapse occurs, as long as it goes to the event horizon, we will think of the simplest possible structure, which is a collapsing spherical shell. So we are thinking of a shell, a thin shell of matter, which is collapsing to form a black hole. So we begin with, let us say, a shell which has some mass m and it has some radius r. Okay? And it is collapsing inwards. Now, think of it physically as somewhere here and it is collapsing. And in the vacuum state, there are modes which are flowing through this. And if I have a mode which is sort of traveling inward and then traveling outward, when it is going in, it is going to have blue shape, and when it is going out, it is going to have red shape. But of course, by the time the mode is traversing through this, the system has collapsed a little bit, which means that there is a net residual redshift for this wave. So the waves are ingoing up to r is equal to 0. At r is equal to 0, they become outgoing, and then they move out to infinity. Now, as this collapses, there is going to be a critical wave, and this can keep happening for quite a bit of time. So let us say by the dotted line, let me indicate here also. Let us say this is the short sail radius, this is 2m. So originally the shell was outside its short sail radius, and at some stage it is just getting close to its short sail radius. Once the shell has crossed the short sail radius, the ingoing mode cannot escape out. So the modes which I am going to detect at late times from infinity, very redshifted waves. So it starts with some frequency and then its wavelength keeps getting elongated. These modes, what I should concentrate on are the modes which are going to come to infinity, escaping out of this collapsing structure just when it is very close to r is equal to 2. So if you want to do the mathematics rigorously, you start with an ingoing mode. First you match it when it crosses the surface, then you reflect it at r is equal to 0, then you match it again at this surface and you take it outside. Now all this matching just makes mathematics more complicated. All the physical effect comes from the fact that the modes which I am going to catch at very late times, at a very large distance from the body, are those which have escaped the collapsing structure just when it is crossing r is equal to 2. So the mathematics is contained in what is the kind of redshift or the time dependence of those modes, which I want to derive for you. So in order to do that, let us again take the metric, and the metric here can be written as that standard form which I told you. So ds square is something like minus f of r dt square plus dr square upon f of r plus some transverse coefficients. Now I am interested in looking at the radial trajectories of the rays in this space-time. So that if they are massless modes, and in fact if it is massive also near r is equal to 2 and the mass time gets suppressed, the massless modes, they are given by just putting ds square equals 0. So ds square equals 0 is like, think of it like photon. The photon path is given by that. So the trajectory of those rays are given by dt upon dr, the whole square, equals 1 by f square. In other words, t at the time of reception minus t at the time of emission is given by integral over dr upon f of r from r at the time of emission and r at the time of reception. So you are thinking of a mode which is escaping from here to infinity. There is a point at which it is received. This is the point at which it is this picture. This is the point at which it is emitted, which is just next to r is equal to 2m, or the singularity, or the horizon. So this integral is going to be dominated by the contribution near this point, because this RE is very close to the horizon, and the horizon occurs at r is equal to 8. So I will approximate this by integral RE to R dr. F of r I can approximate as f prime at a into r minus a. Now f prime is what we have been calling 2 kappa. So this is 2 kappa r minus a. So if you integrate this, you get essentially 1 upon 2 kappa log r minus a, and I will normalize it by dividing by a. So this is the leading contribution to the integral, which relates the place where it is being emitted to the time at which it is being received. Okay? Now I also want to know what is the redshift of this wave. So the redshift is given by the following formula. If I look at omega, the frequency of a wave at, let us say, infinity, divided by the frequency of the wave at some point r, it is going from some point r to infinity, and it should get redshifted. So this is going to be square root of g naught naught at r divided by unity, if g naught naught is 1 at that point. Okay, just want to make sure that this is going to be a factor less than unity, so this is omega at r is reduced to omega at infinity. This is the result which you have. So this is going to be equal to square root of f of r in this particular case. Therefore, we can write this as, and f of r also we have the standard approximation. You get this as square root of 2 kappa r minus a. From this you find that the 2 kappa t minus t emission, exponential of that, is given by, sorry, there is a minus sign here because this integral is coming from the lower limit. So this is minus 2 kappa t minus t is given by r minus a by a, which is 1 by a, and you have to get r minus a, which I can obtain from this. This is omega at infinity upon omega at the time of emission, this side, square of that into 1 upon 2 kappa. We are all done. So now you simplify everything. All that you have to concentrate on is this omega infinity and this factor. So except for constants, you get the result that omega infinity goes as exponential minus kappa t. There are a whole lot of constants, it doesn't matter. There is a minus 2 kappa t here, and you take the square root, that becomes minus kappa t. Okay? What does it mean? What we have shown is that when there are wave modes which are entering and leaving this collapsing structure, the wave modes which you are going to detect at very late times are those which has been leaving the body just when it was crossing r is equal to e, where the horizon is. And the near horizon behavior I can approximate by this method, and once I have done that, I can relate the time dependence of the frequency of the modes which I am going to see by this relation. It tells you that at late time, the frequency which I am going to detect is going to be exponentially redshifted with an exponential minus kappa. So if I now go back and redo my analysis, and I say that I am sitting quietly at a faraway point from the black hole, and I should use modes which are going as e to the minus I omega t, but it is going as at e to the minus I exponential minus kappa t. I do the Fourier transform, and I'll find that the negative frequency modes that gives me a power spectrum which is blank. This is the main theme which I did in the first lecture itself, once and for all, that whenever there is an exponential redshift, if you do the power spectrum, you will get a thermostat. At that time, somebody, I think you raised the question, that where are these waves? Because I used a classical wave. But the waves are provided by the quantum field. So the quantum field has modes which are going in and going out, and they do not balance each other in the presence of a collapsing structure, and there is a net redshift, and that net redshift is what gives you this. Now you can do a more sophisticated analysis of the same problem by calculating what is known as the expectation value of the stress tensor of the system. Then you will find that there is actually a flux. That should be sort of obvious from here, but if not, you can actually formally compute it, and you will find that there is a net flux of radiation which is coming to infinity and which has the same temperature as this. Okay? So what we have shown is that there are two different contexts in which the temperature appears in the black hole spacetime. One is an eternal black hole, which is a time-symmetric state where nothing is changing with time, and that is in thermal equilibrium. If you put a scalar field in that, that scalar field will reach a thermal equilibrium with a temperature which is given by tau kappa over 2 pi. On the other hand, if you have real matter which is collapsing to form a black hole, then at very late times, during the early time there are all kinds of transients, at very late times you will see a steady flux of radiation from that body, just like light from the sun, with a Planckian spectrum, and that temperature will also be kappa over 2. The analogy in the case of Grindler frame, which I gave you, is for two different cases. One is a steady, constant acceleration all the way from minus to plus infinity. That is a thermal equilibrium state. If you take G to be a function of time, GFT, and then you do the analysis, the initially plane wave modes, which set up your inertial vacuum state, at late times get populated by particles, which corresponds to the same temperature. So the variable acceleration should be thought of as analogous to a collapsing structure. Okay? Now I want to do just one more thing before we disperse for the day. And this is something which you won't find in textbooks, but I have been highlighting it in some of my papers, and this is an extremely peculiar relationship which comes in all these analyses. All that we have done so far never used Einstein's equations, because I haven't even mentioned Einstein's equations in this. Of course, I took a class of metrics, f of r. I said that it should have a 0 at some r is equal to a, and then Taylor expanded around r is equal to a. But I did not demand that that metric with that f of r should be a solution to any field equation. It happens to be a solution to Einstein's equation, but I don't care. I would have done this with any theory, any metric, and given a metric and you put a scalar field on that space-time, you get the thermal behavior. The analysis used an external field, and the external field had the temperature. Now this raises a lot of conceptual questions. I say that there is a temperature. It is the temperature of what? Is it the temperature of the space-time? Is it the temperature of the horizon? Or is it the temperature of the scalar field? So if there is no scalar field, is there a temperature? Second, where does the dynamics come? I mean, suppose the theory is not given by Einstein's theory but some other theory, and I have the same metric. Do I get the same result? Because I can start from the metric, put the scalar field and obtain the same result. So how come this is completely independent of dynamics? So now I want to show you a very weird connection which comes up in these models, for which there is no fundamental explanation in the conventional approach. Okay, but I think you should be aware of that, so let me do this. So to do that, again we will start with the metric which I have written down there, that f of r dt square plus dr square upon f of r, and we will explicitly write down Einstein's equations. Okay, we will write down what is the Einstein's equations for this system. So the source we will assume is made of some energy density and pressure, and I am assuming spherical symmetry, which means that the source components has to, the energy momentum tensor of the source has to satisfy some particular relations, which we will assume holds. If you do all that, then you find that there is only one non-trivial equation which you have to solve. That equation happens to be the following. So let me write it down. This is textbook. You can take any standard. This part is you can find from any textbook. You will find that the equation is 1 minus f of r minus r f prime of r should be equal to minus 8 pi g over C4. I need all the C's and H crosses explicitly put in here for a particular purpose. You will see very soon. P r square. So if you take your favorite GR text and look at the spherically symmetric solution section, you will find this equation. This is one of the Einstein's equations which you have to solve. The P here is the radial pressure. Okay, the space-time is not isotropic, it is spherically symmetric. So there are radial pressure of the matter. That could be zero if there is no pressure, but otherwise this is the radial pressure. Now I want to evaluate this equation on the horizon, that is at r is equal to a. So at r is equal to a, this vanishes because f is equal to, sorry, on r is equal to a, this f vanishes. So you have only one here, and then this becomes a and this becomes f prime of a. So I can rewrite this in a slightly different way in the following form. C4 upon G half f prime of a times a minus half equals 4 pi a square p. This is done in order to get that 4 pi a square p. So I multiply by this C4 and G to this side. This f goes away. This 1, because I am keeping a 4 pi, that's a factor half, that comes in here. And this gives you this f prime of a. Okay? Now let us rewrite this in a slightly different way. C4 by G, first term, and f prime I know is 2 kappa, but let me not do that yet. So this is 2 a f prime of a minus C4 over 2G equals 4 pi a square p. Having done that, I am going to multiply this equation by an infinitesimal increment in a dA. So I just put a dA here, I will put a dA here, and I will put a dA here. What does that mean? You can think of it as purely a mathematical exercise. On the other hand, you can think of it as having two Einstein solutions with horizons at a and a plus dA, and I write down the equations for both and I subtract one from the other. So this is the lowest order change in this. Then I also know that the temperature of this, just from Euclidean periodicity, again with all the constants thrown in, is given by h cross c f prime of a divided by 4 pi. This is essentially your kappa over 2 pi formula, because f prime by 2 is kappa and h cross c and everything else should have been constant. I have an f prime here and I want to get this introduced there. So what I am going to do is to take that term, I have a dA, then I have a C4 over 2G A f prime of a. Now I am going to multiply both numerator and denominator by h cross on an otherwise completely classical equation. Take one c cube, keep one c cube here, and you multiply a c here, and then also divide this by 4 pi and multiply the whole thing by another 4 pi. This is the first term. Second time I don't have to do anything. C4 by 2G d equals, that I write as PD. V is what is known as the areal volume of spherically symmetric surfaces, which is 4 pi s square dA gives me the volume element. So the right hand side looks very nice. It looks like PdV. Now this F prime h cross C upon 4 pi we know is temperature. So this is T. So it looks very likely that this quantity is ds and this quantity is dE. If I make this identification, I have no choices because PdV is fixed, T is fixed, so the coefficient of this I call ds and this I call dE. Then I just read off what E and S are. So S is, you just integrate this, so I have a dA, you integrate this, that will give me S square by 2 pi, and that pi will go away. So you will find that this gives me S is equal to 1/4 of the area of the horizon divided by G h cross upon C cubed, which is the Planck limit square. So I can write it as 1/4 area of the horizon divided by LP square, and E is just half of, I can just integrate this, half of A, okay, with C4 by G. So again, if you set C and G to 1, as we normally do, and A is the horizon radius, which is 2m for the short side, half of 2m is m. So the energy is just mc square. And if you throw in all of them, the dimensions will take care of themselves. Now this is what I said is a very mysterious relation. Here we are starting from Einstein's equation. I didn't do any quantum field theory. And from Einstein's theory, I just evaluate Einstein's equation on the horizon, which is what I have done here. That is this. Then I multiplied it by dA. Then I just transformed the equation. I just did some algebraic jugglery in order to make the right hand side read PdV. The moment right hand side has the PdV structure, I have no further freedom left because I know precisely what the temperature is. That I don't need anything else. From the Euclidean periodicity of this metric, I know that the temperature is given by that. So I identify this T. So I have a relation which says that PdV equals T times D of something plus D of something. So thermodynamics suggests that we should identify this with S and this with E. And the identification with this E immediately makes sense, at least for short side. And if you look at any other black hole, it turns out to be what is known as the irreducible mass of the black hole, which is considered to be the intrinsic energy of the black hole, whether rotating, this, that, etc. And the entropy of the black hole from that turns out to be this, which is 1/4 of the area of the horizon in Planck units. The question is, what is the connection between this and the original result which I obtained using quantum field theory in that background? Nobody has found a connection, and it is almost impossible to obtain one. Because to begin with, this expression had this interesting introduction of h cross here and here. The final expression is independent of h cross because it only uses TdS. So I could have multiplied this by some alpha and some alpha here, but I know what the temperature is from an independent T. This is the only quantum mechanical input which has gone in, which is the periodicity in the Euclidean time. But I have never assumed Einstein's equations in the previous derivation. Here, this comes out of applying Einstein's equations on the horizon. If Einstein's equations were not correct, you would have thought that this equation will not hold true. So when we first discovered this, We said, oh, okay, that shows a connection between Einstein's equations and thermodynamics. So let us see what happens in some other theory. So there is a host of theories of gravity which is available. Almost all of them has black hole solutions, and for almost all of them people have worked out thermodynamics. We found that this relation holds in every theory to which it can be tested. So by now it has been examined for a vast class of solutions like Lovelock models, models with f of r kind of gravity, models with a scalar field coupled to gravity, etc. Whenever there is a black hole solution and you do the conventional analysis and identify what is the temperature, what is the entropy. Entropy is not always 1/4 of the area for such theories. It will be a more complicated expression. But whatever that expression is, Einstein's the field equation, which is also different, arranges itself in such a way that the TdS equals dE plus PdV is identical to the field equations evaluated on the graphs. So as I said, this is a mystery and this is a problem worth tackling, and I have been working on this on an alternative perspective where this emerges very naturally, where you start with a thermodynamic underpinning for gravitational theories and where this is the starting point, and from that you can maximize the entropy, etc., and get the field equation. But I thought I should mention it to you because this is, as I said, is one of the intriguing points in that whole derivation. And there are several other issues like what is the entropy which we are talking about. So this is one way of introducing the entropy, and you can, yeah.
Yes, a comment. So here, I mean, I think it's important that again here when you assume all these theories of gravity, when you assume these theories of gravity, they are theories of gravity with Lorentz invariance.
They are theories of gravity.
Where Lorentz invariance is.
Okay.
So
there is a
possibilities of breaking them.
Okay, there is a paper on the web today by Rongchen Kai, which says that in the Horova is not a correct pronunciation, but that is how it is spelled, Horova-Lifshitz series, which does break general covariance, the equation still holds. Okay, so it is much deeper than even the. Yeah. So I don't know of any other model in which all the models I know maintains diffeomorphism invariance. In all theories which has diffeomorphism invariance, one can show that this result follows. Yeah. The first example which I know where diffeomorphism invariance is not maintained but still this equation holds is the paper which appeared yesterday or today. I haven't studied it in detail. Okay, so it seems to be slightly deeper and I have to understand that. Yeah. But in any theory with diffeomorphism invariance, one can show that this holds, but that is a much larger class of theories than Einstein's theory. Okay, so that is what is happening. But I told you that this is one way of getting the entropy, but yeah.
Sorry, the element of volume that you considered here is a coordinate volume.
Yeah. Okay, so that is a good point. It is not a proper volume, but in fact you should not think of it as volume. The way the physical picture works is you think of the black hole horizon as some kind of a membrane. There is a membrane paradigm for black hole horizon. And you think of pushing that, doing some virtual work. Then what you should do is to take the proper area, not the proper volume, proper area, multiply by the displacement. So it is much better to think of it as 4 pi s square dAp. That is the way I would think of.
Well, displacement should be proper displacement. Or
no, the displacement should be coordinate displacement. Because I am thinking of two different radii at which the horizon is occurring. Right? So that is what is happening here. So, of course, you can ask what happens with proper displacement. We have fooled around with it. That is, you put the proper displacement or a proper volume and see what corrections turns up. It becomes horrible. It doesn't make sense. So it seems to pick up this 4 pi s square times p as the kind of a pressure which is acting on that proper area. And then this dA is just the change in the radius. Okay, that is what maths tells you. Okay, it is not a proper volume. That point is well taken, and it is noticed in the literature, and people are worried about it. But one doesn't have a simple explanation for that. Okay, so this way of deriving the entropy is one attempt. But how do people normally derive it in a conventional way? That is very easy. What you do is that you said there is a black hole which is emitting radiation with some temperature T. Then you can ask how much energy it is losing. So you compute dE by dt. which you can calculate to be proportional to the area of the black hole surface, which goes as m square, times the temperature. So if you work out the surface gravity in this particular case, it will go as some 1 over 8 pi m. Okay, so you get a result here that this goes as some m or whatever, and from that you can calculate how the energy of the black hole is changing. In particular, if you now write some T ds equals dE and identify the energy with the mass, this T is going to be 1 over 8 pi m times ds, and you can integrate this to get S to be the integral of this, which will be 4 pi m square, which is 1/4 of 4 pi 2 m whole square. Okay, this is the conventional derivation. But there is a little bit of a trickery involved here. We started with a black hole spacetime in which m is a parameter. Then we put a quantum field in it and we asked how the quantum field behaves in the early times compared to late times, and we found that this quantum field is behaving as though there is a flux of radiation to infinity. Okay? That is fine. So there is a flux of radiation to infinity. But then you ask, where does this energy for this flux is coming? The only source of energy which is available to you is this mass, the parameter mass in that. Then you say that this mass has to change. But originally we were working in a test particle approximation, so to speak, where the background is fixed and the field is on that. But you want to now go one order away from it and say that the result should hold even when m is changing, presumably slowly. Then you can write dm and say that is equal to Tds and do this integral and obtain that result. The reason I emphasize this is that there is a slight peculiarity here. This was again pointed out in the previous lecture, maybe by you, that if you write the Kruskal metric and when you let the short-sailed radius Rg go to 0, it is non-analytic in Rg, so it actually sort of behaves singularly. You do not get back the flat spacetime. So you can ask, what is the entropy and temperature of the flat spacetime? You start with the short-sailed metric and you put m is equal to 0, you get flat spacetime. So I could have done the thermodynamics also in the same way and taken the limit. What you find is that the entropy of the flat spacetime actually goes to 0 when m goes to 0, but the temperature of the flat spacetime goes up. So viewed as a limiting sequence of m going to 0 limit, flat spacetime has the infinite temperature, not 0 temperature, but it has 0 entropy, which is a little bit weird. So that is another point which has to be borne in mind when one is interpreting this. And many of these issues are still very, very uncertain. In particular, the entropy of any of the horizons, Rinder, de Sitter, black hole, any of these horizons, where it resides, what is it due to, what are the modes which are contributing to it, what is the relation to the temperature, is still an uncertainty. So I think I will stop with that too.
Thank you.